be 2.5, or it could be earlier, right? Selena.
Can you just go over what the that one theorem is? The
Squeeze theorem or intermediate value theorem?
intermediate, that one.
Okay.
Thank you.
Yeah, so I'm just gonna talk for a minute, like with some pictures, and then we'll do like something with an example. So what this is saying is, if I have some function that's continuous on the closed interval from a to b, and I pick some y value that's in between, say, like f of a and f of b, there's got to be at least some x between a and b, where if I plug that into f, I get that desired y value, right? So it says that, like, if f is continuous on AB, then we should probably say with, f of A less than f of B, then there exists a C on the interval open interval from A to B, such that f of A is less than k is less than f of B was, and such that f of C is equal to k. So that's basically what it's saying. And just saying that, like, if I have some function that's continuous over some interval, and the y coordinate at the start and end of the interval are different, they gotta be different, then if you pick any y in between those two, I can find some x on that interval that'll output that y. So that's the idea. So like if I have, say, a table of values here, and let's just say f is continuous. And say these are my y values. And I ask you, like, okay, how many times does f cross the x-axis? So basically I'm looking at how many times does f of x equal 0, right? Well, it's got to cross once here, going from negative to positive. It's got to cross once here, going from positive to negative. And then it's got to cross once here, going from negative back to positive. Now, do I know it doesn't cross like 2 or 3 or 4 times in between there? I don't. Do I know it doesn't cross somewhere, cross 0 there? I don't know that. So I would say, like, at least 3 times. And the reason I'm able to guarantee that is the intermediate value theorem guarantees there's a 0 in each one of these little intervals, because 0 is that y value. So I know there's an x in between 1 and 2, that f of x is 0. That's kind of what we're saying. Does that?
Yeah, that. I think.
Yeah, so don't get, like, the notation is tough, but the idea is simple. Like when you draw the picture and explain what it's saying, it's like, okay. And if you have to say it in words, like if you don't like the notation, just say it in words. You can just use words. That's okay. Like whoever is the IB grader will read it, and it'll be okay. If you have to use words, use words. If you're good with symbols, do symbols. I won't grade you down as long as the wording is, is correct or precise enough or whatever. Is that good? Okay. Other questions, again, they can be general, like, can we talk about this idea a little bit more? Or they can be specific, like a homework problem. That's fine. Either is okay. Alex? 54 from 2.5? Okay. All right, so 54 says use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So when we say root, that's the same thing as a solution, right? So what I would do is I would start by moving everything onto one side. So like that. And then I'm going to say let f of x equal that right-hand side. I'm going to note that f of x is continuous. Why can I say that? Before I start using the intermediate value theorem, I have to show continuity on f of x. If I don't have that, nothing else matters. Okay, so because it's the sum of a polynomial and a sine function, right? Both of those are continuous, so we're continuous. We've taken care of that. It's just a statement. You don't have to prove it because we've been given like this list of types of functions are continuous. Great. Next, what I need to do is I need to find a y-coordinate that's negative and a y-coordinate that's positive on that interval from 1 to 2. So if I do f of 1, so I can say that. Now, what's sine of 1 without your calculator? Don't give me a number. Is it positive or negative? Positive. Very good. Because I know sine is positive from 0 to pi, because that's going to cover the first 2 quadrants on my unit circle, correct? 1 is definitely less than pi, so I know that sine of 1 is positive, so I know negative sine of 1 is negative. Everybody's cool? If I do f of 2, is 2 minus sine of 2 positive or negative? Again, without a calculator. Has to be positive. How do I know that? The biggest that sine could be, or the biggest sine of 2 could be is 1. 2 minus 1 will still be positive, right? Could it be less than 1? Sure. If it is, 2 minus that's still going to be positive. So we're good, right? We've accomplished what we're looking for. So we can say since f of 1 is less than 0 is less than f of 2 by the intermediate value theorem, there exists C on the open interval from 1 to 2 such that f of C is equal to 0. And we're done. We've shown there's some C there. Now, if you had access to your calculator, could you just graph both sides and found the intersection between 1 and 2? Are we actually looking for the value of x, though? No. And I don't know that we've talked about this yet. On the AP exam, the format for the AP exam, you have 4 sections. So you have multiple choice with a calculator, multiple choice without a calculator. Free response with a calculator, free response without a calculator. In almost every single setting in this class, I'm going to show you, or at least talk about both ways to do something. Now, in a question where it's asking you to use the intermediate value theorem, that screams no calculator to me. Would be a no calculator section question. But if they're asking for the root, I mean, it's just like, I'm going to use my calculator, just graph and find the intersection. There it is. Some answer between 1 and 2, good enough, done. But notice that it doesn't need that level of specificity in the direction. It just wants the existence that there's a root. That'll do it, right? Yeah. Yeah. Michael. 12? Sure. Same section?
Yep.
Okay. So 12 says, use the definition of continuity and the properties of limits to show that the function is continuous at the given number a. So to do this, I need to show 3 things, right? I need to show that the left-hand limit equals the right-hand limit equals the function evaluated at that value. Now, if I look at this, I want to find out right away if I can do direct substitution to evaluate these limits. Because if I can, that makes my life massively easier. In order to use direct substitution, I need a function that's continuous over its domain. What do you guys think? Yes, right? Polynomial plus a cube root is 2 functions that are continuous over all, or defined over all real numbers. So this is also going to be defined over all real numbers. So that'll work. So this is just going to be f of 2. This is going to be f of 2. Well, and that's clearly f of 2. So we're kind of done. Now you could plug those things through if you wanted to, but like that's the idea.
Say like that, you just plug in.
Yeah. Yeah, that's all I mean. Plug in 2 in for x for f. But it said to use the definition of continuity, so I wanted to write down what I was trying to show. Alex?
What would f of 2 have to equal for it to not be continuous?
Well, if any one of those equalities failed at any of those spots, if it was something other than f of 2, or if f of 2 was like undefined or something, well, you couldn't do direct substitution for the limit if f of 2 was undefined. But if I plug 2 into f proper and it's undefined, you know, like, so if any of those if any of that equality fails, you know, if it's, you know, if the first one gives you 2 and the next one gives you 3 and the third one gives you 3, well, that doesn't work. They all have to be equal, right? So you just, anything that's different. Is that, Michael, are you happy with that idea? Again, I didn't work it all the way out, but I feel like I did enough for like, you can take it from here. Usually short of number crunching, I'll have no problem doing the whole thing, but at the end of the day, I was like, I don't want to plug all that in. Others, questions from homework? Or other questions? Okay, very good. I started doing this one day and then I felt like I was doing it wrong and we stopped. You remember when I was doing this? I wasn't doing anything wrong, which is great. Everything that we had said was correct. So the way we were doing this was perfectly fine, doing these compositions. I just didn't get to the one where it's the tricky one. So I was confused because it was easy and it's like this, why is this not the problematic one? So let's look at this one. So if we're doing the limit as x approaches 0 of f of x, ideally what we'd like to be able to say is this, right? Would you agree? And what's the limit as x approaches 0 for f of x? 2. And what's f of 2? Would be 1. That's not right. And the reason we have to be careful here is because you're plugging it into a discontinuity, right? If I was plugging 2 into, or if I was plugging a number into f where we're continuous, what we've done is fine. Because there's a discontinuity there, it's not. So this is, oops, let's use a color. So that's not that doesn't work. What I want to look at is doing it this way. So we do this, and look at what is happening here. The limit as x approaches 0 of f of x. We're approaching 2 from below, right? So this is really going to equal the limit as x approaches 2 from below of f of x. And what is the limit as x approaches 2 from below? It's that end. Yes.
Is the negative or the negative for like limit for 2, is that?
That's like the superscript.
The superscript. Is that like for the left and for the bottom?
So it just means, I like to say from below. So if you're looking up and down, that's underneath. If you're looking on the x, that's like the left. So it's, like if I look at f as it's approaching 0, either side we're coming from a number that's less than 2. Correct? So when we're plugging that number that's approaching 2 but still less than 2 into f, it's like doing the limit as x approaches 2 from below of f, right? Does that?
Yeah.
Okay. Now, is this always going to be possible to get an answer? So if we have this graph and we do the same thing, I try to do what we did before. So we try to push our limit inside. And that limit is 2, right? But that's happening at a discontinuity, so I know I can't just plug that in. I can't just plug the 2 in, right? You guys see that? Because it's plugging it into a discontinuity. Bad. So if I try to do the same thing, though, the limit as x approaches 0, y approaches 2 from the below and from above, correct? So that doesn't help me at all, does it? On picking which end of my jump discontinuity to use to do the next limit. So it just can't do it. Doesn't exist. So that's the catch, is when you try to do this pushing the limit inside of our function, it's all well and good until what you're trying to plug in then is at a discontinuity. If it's at a discontinuity, you have to be careful. So it's either if you're at a relative extrema, you can do it. You can use that extrema to tell which end of your jump discontinuity to use. But if it's not at a relative extrema, can't do it at all. Does that feel okay? Let's do 2.6 then. And that'll be the last section we're going to look at before the first test. Yes, sir.
Sorry, can you like go back one second?
Of course.
But isn't there, like in the one above, isn't there also a discontinuity at 2?
Yes. And it's okay because I know that I'm only coming and using that end of the discontinuity. Right? From this one, I have this, which is pointing to this end, but I also have this, which is kind of going at that end. So the limit doesn't really agree, so we said it does not exist. Like on this one, we have coming from here, which is that end, and then there, which is also that end. That's why we can do it. Does that, seeing the picture, help at all? That's not very convincing. So here's, remember that a limit doesn't exist if it's left hand and right hand limits disagree, right? So if I look at plugging in this 2, if I'm looking at the left hand limit, that's saying we're heading at 2 from below. If I look at the right hand limit, that's also heading to 2 from below. So that is agreeing. It's saying that should be my limit. If I look at this one, I head for 2 from above. Oops, I have these on the wrong ends, huh? So that's this one. And if I attack 2 from below, that would be going to this one. And those are 2 different limits I'm getting from the left and right hand. So that's why it doesn't exist.
So it's like the ones on the bottom, right? It's the ones on the bottom, or the blue one out there.
Yes. Yeah, that right here it's disagreeing, right? Because they're going to 2 different limits. That's why it doesn't exist on this one. For the previous one it did. The easy way to look at this, Michael, though, is if I'm plugging into a discontinuity, the thing I have to be plugging in has to be an extrema, a min or a max. If it's not a min or a max, it's just not going to work. So like here, 2 is not at a minimum, or I'm sorry, x equals 0, there's no min or max there. So if I'm plugging that in to the next spot, and that next spot's at a discontinuity, it won't work. The previous one is at an extrema. So if that value is going into a discontinuity, that I can do. And I know should I take the left end or right end if it's a max versus a min. And that's basically the gist of it. Does that? Okay. Yes.
So if it was a minimum, it'd be the limit from the right.
You'd be taking the top.
Okay.
Yeah. Or the right hand. Yes.
Okay.
Yes, exactly right. 100%. Is that better?
Yeah.
Okay. 2.6, here's the good news. This is all stuff you know already. We're just going to formalize it using limits. Okay? So all we're talking about here are vertical and horizontal asymptotes, which you've done. Which you know how to do. You know what this is. So the first thing we're going to do is we're going to define the idea of a limit at infinity. So here we have the limit as x approaches infinity of f of x equal to L. This is a limit at infinity because the x approaches is going to an infinity. It could be positive or negative, but that means we can make x as big as we want, but the y is just going to be settling down at L. Right? So if I looked at an xy table, it might say like 1, 2.5, 10, 2.8, 100, 2.86, 1,000, 2.9, 10,000, 2.97, and it's getting closer and closer to 3, but we're never actually going to get there. You guys get the idea? And this should look familiar, right? We saw the same thing when you guys would have done like rational functions and talking about asymptotes, or exponential functions and talking about horizontal asymptotes last year. So again, we have that limit can kind of exist 3 different ways, right? We can approach that limit from below, we can approach that limit from above, or we can kind of approach that limit from an oscillating, where it's kind of, starting off big and then just settling down, but it's always bouncing back and forth above and below, above and below, above and below. Everybody's okay with that? And this would be like 1 over x times sine or something would give you something that looked like this. So we say the same thing if x approaches negative infinity. And this is how we're going to define a horizontal asymptote. So we say that something is a horizontal asymptote if, the line y equals L is a horizontal asymptote if either the limit going to positive infinity gives you L, or the limit going to negative infinity approaches L. Everybody's okay with that? One thing to state here, and maybe this isn't obvious, you can have 2 different horizontal asymptotes if the limit to negative infinity goes to one number and the limit to positive infinity goes to another number. Do you guys remember a function from last year that has 2 different horizontal asymptotes to it? Not sine or tangent, a logistic function. Like 1 over 1 plus e to the x. No, that's okay. It just means you have an exponential in the denominator. So like 1 over 1 plus e to the x. If you look at that on your calculator, I'm going to use this grapher because it'll give me a better picture. So you see we're getting 2 different horizontal asymptotes, one at 1 and one at 0. So that's, canonically, that's your example of something that would have 2 different horizontal asymptotes. That's not piecewise. Obviously, if I make something piecewise, I could very easily get it. right? So from a definitional, tan inverse, maybe that's what we were thinking. Somebody said tangent back here, right? Tan inverse also has two different horizontal asymptotes, right? Because you remember one period of tangent looks like this. So when you like to rotate it, you have that guy. It has two different two horizontal asymptotes too, also at negative pi over 2 and positive pi over 2. That sound right? Okay. All right. Let's take a look at this picture here. What do we see here as far as our horizontal asymptotes go? The limit as x approaches negative infinity goes to 2. The limit as x approaches positive infinity goes to 4. And then we see some other infinite limits also, right? We see this, well, this and this, right? So what else can we say? We can say limit as x approaches negative 1 of f of x goes to positive infinity. And we can say the limit as x approaches 2 from the left of f of x, that goes to negative infinity. And the limit as x approaches 2 from the right of f of x goes to positive infinity. Does everybody feel okay about that? Remember that these guys, yes, sir.
Where's the x equals 4?
That's that piece. Remember that if you have a limit that's going to either positive or negative infinity, that means it's also a vertical asymptote, right? That was our definition from section 3, I think. Oh, we just did that. Nah. All right. Let's look at the limit as x approaches infinity of x and x approaches negative infinity of x. Let's try to do this without a calculator. Obviously, you could use a calculator to look at the graph. Not wrong to do that. So let's look at what happens when we plug in progressively bigger and bigger numbers to 1 over x. So when I plug 2 in, what do I get as a decimal? When I plug 4 in, what do I get as a decimal? When I plug 8 in, 0.125. Great. What are you noticing? Getting smaller. Is it going to get smaller indefinitely? Without bound? It's going to become negative? No. It's going to go to 0. Yeah. Very good. Now, what happens if I plug in negative 2? What do I get? Negative 0.5. Plug in negative 4. And then negative 8. And what are we going towards? 0. Just we're going from approaching 0 from below. The first one we're going to 0 from above, right? But they're both going to 0. Everybody agree? So we have a horizontal asymptote at y equals 0. We should get in the habit of writing y equals or x equals because we'll have both vertical and horizontal. So everybody's good? Okay. So let's generalize this. If I take the limit as x goes to infinity of any power of x, well, I should say any rational number power of x, that limit is going to 0. And if I do the same thing, x going to negative infinity, any rational power of x goes to 0. Actually, we should say positive rational value of x. Right? If it's negative, it flips it to the top. That's a whole different ballgame. Everybody's okay here? So just a generalization of what we observed previously. We'll use this as a theorem to be able to do stuff here in a moment. So what if we do something like this? Well, this is algebraically what we're doing. But then I'm going to remind you that you already know how to do the answer to this without doing anything. So I'm going to multiply the top and bottom by 1 over x squared. So in doing that, I have 3 minus 1 over x minus 2 over x squared. And then I have 5 plus 4 over x plus 1 over x squared. Everybody's okay with what I did to there, algebraically? Now I can use my limit laws. So I'm going to distribute my limit and pull out any constants. Is everybody okay with what I did there? Okay. This limit is 0. We just did it, right? This limit is 0. This limit is, and this limit is, okay. And then what's the limit of as x, or what's the limit at 3? Limit of a constant is just a constant, right? Hold on, I'm going to get there. That's 3/5, right? Now, who remembers the rule from pre-calculus? You should be able to look at this and tell what the horizontal asymptote was going to be. 1, how did I know there's going to be a horizontal asymptote? Same degree polynomial. When it's the same degree polynomial, how do you find the asymptote? Leading coefficient over leading coefficient, right? Does that sound familiar? What happens if the degree of the denominator was bigger? It's 0. The horizontal asymptote is 0. What happens if the numerator is bigger? You have that slant asymptote, right? You don't have a vertical or horizontal. You have that like diagonal asymptote. How do you find that? Polynomial division. I know, that's rough. Just reminding you the rules from pre-calculus, because if I don't have to do what I just did there and like muck around with all that algebra, if this is a multiple choice question, I want to be able to look at it and write down the answer. That's preference, right? Because the test is timed. I want to be able to look at it and write down an answer. That helps enormously. You know what I'm saying? Okay. Let's look at this guy. So find the vertical and horizontal asymptotes for this. From last year, how would you find the vertical asymptote? Root 2 over 3. Well, the square root's only applying to the numerator.
Yeah, but I was saying it would get rid of the square and it would make the root 2 x. So root 2 over 3.
Ooh. I don't think so. We set the denominator equal to 0, right? What do we get when the denominator is set equal to 0 and solved? 5/3, right? Everybody agree? Now, guess what? Oh, you're giving me the horizontal.
Yeah.
I misunderstood what you're trying to give me. Root 2 over 3 is correct.
Okay.
So very good. My apologies. All right. That is correct. Can anybody see how we did that? So if we're taking the limit to positive infinity, does the plus 1 here really matter if x is going to infinity? Nope. So this limit's going to be the same as that, right? And if I simplify that down, we found a polynomial with equal degree. So it's just leading coefficient over leading coefficient. Because if x is going to infinity, does adding 1 to infinity do anything? No, right? Like that constant doesn't need to be there. It's going to be the same whether I'm going to have the same limit if it's there or if it's not. Now, this is a trick we can only apply if the x is going to positive or negative infinity, right? Can only apply in that case, but certainly we can use it. Elena. Oh, yes, go ahead. That feel okay? Again, like showing you the tricks, talking through some of this stuff and the reasoning, right? How about this one? What do you guys say? 1? Well, we're just asking for a limit here, right? Just wants the limit as x approaches infinity. This is 0. This is 0. Would you like to see why? Yeah. So again, I'm going to make the same argument. Since x is going to positive infinity, that plus 1 doesn't really need to be there. If I simplify the square root of x, that's just x minus x is, so we just have the limit of a constant at 0.
So you can just get rid of that.
Only if your limit is going to positive infinity or negative infinity. In that case, a constant plus a variable, the constant doesn't matter. Because if you're talking about plugging like infinity in for x, 1 plus infinity is still infinity. right? Doesn't matter. Michael.
If you want to like show that, just like cross it off.
I would just do exactly the way I've written it. Is this limit is equal to this limit, and then you can simplify from, do your algebra from there. But I think that's okay. Yes.
I know it didn't really matter. We got rid of the -5 that the last problem.
Yes, I could have dropped that as well. It didn't matter to me, so I just left it. But my issue was I needed to simplify the radical, and the -5 in the denominator wasn't getting in the way of that. But absolutely, you could, yeah, absolutely. No, it's a great question, because I didn't do it, and I could have, and she's right, and that's good. It solidifies your thinking. I want to ask questions and make sure I'm thinking about this the right way too, kind of person. So I can definitely appreciate that. Good, that's good. All right. Okay. This is the trickiest one we've seen. So what I'm going to see here is I don't have a limit going to infinity, right? I'd like to create one because I know that the limit as x approaches infinity of arctan, or negative infinity of arctan, is something I have a rule for. Everybody agree? So when I plug in 2 from above to 1 over x minus 2, what value is that approaching? So what I'm saying is, what is that equal to? Well, it's just from the left, or from the right. I'm sorry, just from the right. So that one can exist even if it's infinite, right? It's not 0. So think about it this way. Good, it's positive infinity. Think about it this way, though. If I plug in like 2.1, I get 1 over 0.1, which is 10. If I plug in 2.01, I get 100. If I plug in 2.001, I get 1,000. The closer I'm getting to 2, the bigger this thing is growing, and it's going to grow without bound, because the closer I get to 2, the bigger that thing's going to get, period, right? It's going to infinity. Does that feel okay? So what I'm going to do here is make a change of variable. So I'm going to say this is the same limit as t going to infinity of arctan of t. Because this is like plugging in infinity into here, right? That's what this part is saying. So I'm just going to replace that whole interior with a new variable. I'll call it t or y or a or whatever. And we'll have the limit going to positive infinity. And this is now something I have a formula for, right? This is a theorem. We had it back. Where did it go? Here. That it's pi over 2. That's the worst one. Yes, Nate.
So 1 over x minus 2, and then when it's approaching 2 from the right, it's always approaching infinity.
Yeah,
You could just kind of like substitute it.
that's basically kind of what we're saying, yeah. So I replace the 1 over x minus 2 with some other variable and say, okay, we'll take the limit of that variable going to infinity, because that's what, when I plug 2 from the right into 1 over x minus 2, that's what I'd be getting. You know what I'm saying? It's like a substitution. It's exactly the right idea. It's the right way to think about it. Is that okay? The answer is pi over 2. Again, could you have graphed this? If you have access to a calculator, absolutely. You could graph this or look at a table. What is pi over 2 as a decimal? 1.57 or so, yeah. Good one to kind of remember. Okay. The next here is just a statement of fact. X approaches negative infinity of e to the x is 0, right? If I have a negative in my exponent, that makes a reciprocal. So I'm going to have e to the 1 over e to the big, which is a gigantic number. So 1 over a big number goes to 0, right? Does that feel okay? Same thing as saying this, right? Everybody's okay? Equivalent statements. All right. Here we have evaluate the limit as x approaches 0 from the left of e to the 1 over x. I'm going to do the same substitution trick that we just did. So I'm going to look at the limit as x approaches 0 from the left of 1 over x. What is that limit equal to? So you're plugging what kind of numbers into 1 over x, positive or negative? Negative. So this is going to negative infinity. Right, you're plugging in like negative 0.1, negative 0.01, negative 0.001. So you're getting like negative 10, negative 100, negative 1,000. Everybody's cool on seeing that? So now we'll make a substitution. We're just going to replace the 1 over x with a t and send t to negative infinity. And that now is the exact same thing as that previous statement. So we're just going to 0. I'm trying to get to use this. So I need to make my exponent not 1 over x, but just regular x. So I looked at the limit as x approaches negative 0 of 1 over x and got that that's negative infinity. So if I replace the 1 over x with a t and change this going to negative infinity, it's going to be the same thing. If I plug 0 from the left in to 1 over x, I get negative infinity up there, right? Or I could just dump it all out of there and put it a new variable and send that variable to negative infinity. It's doing the same thing. Is that, you see that? It's subtle, it's hard until you like really get used to it. We'll do it a bunch more times. I don't expect you to be a master of it today. Is that okay? And in general, this not a technique you'd use lots and lots of times. The limit as x approaches infinity of sine. What do we think that is? It's not 0. It's what? It's not 1. 1 and negative 1. What is that going to mean then? Close. In limit land, we don't say undefined. We say does not exist. Right, because we know that sign is just going to oscillate up and down, up and down, up and down. It's never going to settle down to a single value. It's always going to bounce back and forth between negative 1 and positive 1. You know, like, you know, just going to keep going forever. Yes, sir.
So at that one at the beginning where like showed that it like oscillated, would it have to like oscillate to the point where it's like going?
Yeah, like it's squeezing down.
Okay.
Yeah, exactly right. That's right on. All right. How about the limit as x approaches infinity of x cubed? What's the graph of x cubed look like? What's the end behavior? Yep. Right? That just go into positive infinity, right? What's the other end going to? Negative infinity. We already knew this, right? Now, any polynomial I can do this for, because I can tell just by the degree of the polynomial if it's odd or even, if you have, and the leading coefficient, like if you have n's pointing up or down, or both pointing up or both pointing down, right? How about this one? Infinity, very good. Again, that's an even polynomial, right? Why did I put this in here? Because if you try to just do a direct substitution here, you'd say infinity minus infinity, and I'd be tempted to bet somebody would have said that equals 0. Can we do a direct substitution with infinities? No. No. Is that, you see why that it's kind of a trick question? But if you just think about it as a polynomial end behavior, easy peasy, right? And this is me here mentioning, hey, indeterminate form, infinity minus infinity isn't 0. Okay. What about this guy here? It's not infinity. Let me tell, negative infinity is the correct answer, yes. Let's see how, right? So, what I'm noticing is the degree of the numerator is less, or is greater than the degree of the denominator, correct? So if I divide these two polynomials, I'm going to get a linear polynomial left. So it's either going to be slope up or slope down. It's either going to go to positive infinity or negative infinity. Everybody's okay with that much? I can tell whether it's going to have slope up or slope down by determining if the leading coefficient is going to be positive or negative. The numerator's leading coefficient is positive. The denominator's leading coefficient is negative. Positive divided by negative is negative. So it's going to be a linear function with negative slope. That's going to go to negative infinity. You know, it's basically going to be the same as like, basically the same as this. Is that okay? All right. All right. Says sketch the graph of y equals yada, yada, yada by finding its intercepts and its limits as x approaches positive infinity and negative infinity. Okay? This shouldn't be too hard, just using what I remember from Algebra 2 and pre-calculus. What are the x-intercepts going to be? 2, -1, and +1. That's correct. And what is the y-intercept going to be? Negative, though, right? Negative 2 to the 4th? Right, it's negative 2 to the 4th, which is just 2 to the 4th, times 1 to the 3rd, times -1. So negative 16. Is everybody okay with how I did that real quick? So I'll just put that down here and I'll label it because it's no longer to scale. Okay. What is the degree of this polynomial? It's degree 4. No, it's not degree 4. It's degree 8. Right? 4 plus 3 plus 1 is 8. Is the leading coefficient positive or negative? Positive. So I know that the end behavior should be doing that, right? Even degree, leading coefficient positive. Now, this guy tells me that I have like a bend going through, so it's going to like do one of those. I come here at 1. That tells me it should be going straight through. And then this one should be a bounce because it's degree 4. And that's good enough. Right? Is that okay? We did them. The x-intercepts and y-intercepts. Oh, sorry. I just didn't connect it. Thank you. Yes, very good. That should connect it. What do you guys think? Today, most of the content was stuff we kind of already knew from Algebra 2 and pre-calculus. Now, some of the limit stuff was tough, but the ideas about like what are the asymptotes here and how do I find the asymptotes quickly without having to do a limit if I don't have to. A lot of that stuff we should remember, at least be like, oh yeah, that sounds familiar. Now you might have to go back and try some and like think about it a little bit, but that's the idea. Okay. So this will be part of Sunday's problem set because we'll be able to meet Friday to talk about this still. We'll have the homework quiz on Friday. I'll take general questions. We'll talk about test format. I'll answer every single question you want to ask me. I'm also going to put a set of multiple choice questions into the OneNote for you guys to practice on. I'll have, okay, hold on a second. Let me ask you this. Would you guys prefer to practice multiple choice questions like on paper or like in the MyAP? Paper seems easier, right?
Yeah.
Okay, I'll drop them into the OneNote then so you can just like have a sheet of paper. You don't have to do them in the OneNote. You can print, you can do it on a separate sheet of paper, whatever. They're just for practice. It's not a homework assignment. I'm not going to pick it out and grade it. But on Friday, I'll put an answer key to go along with those. Because part of every test that we'll take will have some multiple choice questions on all of our tests that'll come from or be similar to the set of multiple choice questions I give you to practice in that chapter. Does that feel okay, Michael?
So is Friday like our day?
Friday will be like our review day. At least that's the plan for right now.
So would the test be Tuesday?
That would be my plan for right now. Now, you're gonna find nobody's had me before, but here's a little thing about Mr. Gulick. I don't care when we do a test. Okay? I'm fine just starting the next stuff. If Tuesday's a very bad day for a vast majority of us, and Thursday's better, I have no problem on Tuesday just starting the next set of stuffs and doing the test on Thursday. Right? So look at your schedules. We'll talk about it again on Friday. I'm going to put the test date as Tuesday on my Notre Dame until we talk about it again. But I honestly, it doesn't make much of a difference to me what day we take the test. If it makes a lot of difference to you, I'm happy to move the schedule around a little bit within reason so that nobody has like an overwhelmingly terrible day. Okay? And I know that like we're all still getting to know each other, but will be always something. If we're talking about a test day or a due date and it's like, Mr. Gulick, that's terrible. Okay, well, just let me know and we can move things around. I'm happy to do that kind of thing. For the most part, I won't fight you on a test date unless it's like, oh, there's only like 2 more times to do this before the end of the semester kind of thing. Or it's like, you really want to push this till after spring break or something. Like, are you really sure? Feels like a really bad idea. Like that kind of thing maybe, but for like a normal whatever, advocate for yourselves. If the day looks terrible and we can reach a consensus that, yeah, that's okay. That's better, or not worse for me. Sure, let's move it. I'm fine doing that kind of thing. Everybody okay in general? How do we feel? Be able to tell me more about how we feel on Friday after you've had a chance to look over some stuff? Okay. Yes, of course.
Wait, so is the multiple choice, is that going to be like a review?
You can treat it kind of like that, yeah.
Like we're not going to get like
I'm not.
a set of questions?
Let me look. I don't know if I have a set of questions kind of made up.
Just to check.
Yeah, just let me look here for a second. So I have this already written out. So format, like skills you should be able to do.
For this test.
Like things to look at. I have my questions. Let me see here. Do I have anything written? I do that on occasion. I don't have anything written for this, though. Oh, maybe I do. What's this? Oh, it's just this. Okay. So that's nothing. Yeah. So sometimes I'll write, depending on like what's going on or what the chapter was, I might write something out. Sometimes I won't. But like, I've given you some recommended problems to go back and look at. So these were things I would have looked at when I was writing the test, and then I gave you the multiple choice stuff to look at. And like all the tests typically get broken into 2 pieces: a calculator, no calculator part. And you'll have the entire class. Yep. So you just do the no calculator part and then turn that part in and pick up your calculator.
Is this test like usually like hard, like this first test?
What I'll say is it tends to be like hot and cold.
Okay.
Right? Like if you're good, you tend to be good. If you're not, it can be kind of rough. is, especially early on, is the stuff we're doing is like, like doesn't require a lot of calculation, a lot of work, a lot of algebra, most of these things. But if you don't understand it well, it's just kind of a nightmare. Is usually what I say. So it just kind of, it varies.
Alright.
It's usually like good or bad.
Yeah.
There's not a lot in the middle this first time through. Does that make sense?
Yeah, I was just wondering.
Yeah, no problem.
All right, thank you.
I'm happy to talk about it.